Welcome to the final talk of this workshop. You already know our next speaker from the first day, Martin Schlipf. In the meantime, you have performed many VASP calculations, some of which took quite some time, although they were designed to be rather quick. You can actually lose a lot of performance when starting up a calculation inefficiently. So I'm pleased to announce that Martin Schlipf will talk about high performance computing with VASP. Martin, the stage is yours.
Thank you for the introduction. So in this lecture, I want to talk a bit more about practical aspects of performing VASP calculations, in particular, how you can set up VASP calculations on HPC machines to get the maximum performance. So let's recap briefly what VASP does in a nutshell so that we understand where we're coming from. So VASP is a plane wave code. That means that all quantities are expressed on a regular grid in real and reciprocal space. So to communicate between the two grids, we use fast Fourier transforms to go from real and to reciprocal space and vice versa. So we need very efficient FFTs. Because this grid is not dense enough to represent a true atomic orbital, we use PAW potentials, where the true atomic orbital is pseudoized, and then we have a construction mechanism to reconstruct the original orbital using projectors. Then we use a reciprocal space technique. This allows us to map the conventional supercell in real space onto multiple independent K points in reciprocal space. And finally, as everybody knows, in density functional theory, it's very crucial to decide what kind of sample or representation of your exchange correlation energy you want to have, from the lowest level of LDA to more advanced methods like meta-GGAs, hybrid functionals, and so on. Okay, so with this overview, I'm coming on to the outline of this lecture. So in this lecture, I want to focus first on the task in VASP, going from this short description to the actual calculations that we need to perform in the code. In the second part, I will then talk about the parallelization of these tasks. So what kind of parameters you can set, how this affects how the calculation is run. And then in the last part, I will talk about some physical and also some hardware considerations that you need to take into account when you choose how to set up your code to run with maximum efficiency. So let's focus on the task at hand. So what we want to solve in density functional theory is this Cohen-Sham equation. So we have the kinetic energy, external potentials, and here the exchange correlation potential applied to an orbital gives you the eigenenergy of this orbital. And to do this in practice, what we want to do is we frequently change between real space and reciprocal space. So often these exchange correlation, this Hartree potential or kinetic energy, for example, are easily evaluated in reciprocal space where they're diagonal. So we frequently change the orbitals to apply this Hamiltonian in the basis that is the most efficient to do it. And to do so, we need to perform fast Fourier transforms on these orbitals. So this is essentially one of the most important costs in plane wave density functional theory. Then we discussed about this, that the plane wave code describes the electronic wave function in a pseudoized form. So this pseudoized orbital is represented on this plane wave grid. And then we have a method, this projector augmented wave method, to reconstruct the true approximate form of this true orbital in this PAW approximation. And to do so, we project this pseudo orbital onto some projectors that are defined in your PAW potential. And this projection then gives us an information about how much of the pseudoized atomic orbital we need to replace with a true atomic orbital. And in this way, we can then recover the true atomic orbital. And this projection method in reciprocal space can be done by a matrix-matrix multiplication. And then for this, we use then efficient blast routines. Then another thing that we need is orthogonal bands. So of course, we want all our eigenstates orthogonal. So to do this, we do an LU decomposition of the overlap matrix. And to do this, we just call a Lapa call and then some matrix-matrix multiplication to rotate this orbitals in these spaces. And another step is then we want the eigenvalues of these orbitals. And for this, we need to do a matrix diagonalization. So essentially, we go from the Hamiltonian expressed in these orbitals, diagonalizing all these orbitals, and we get the eigenvalues and the eigenvectors. And again, to do so, we need Lapa calls and matrix-matrix multiplications. So let's now look at the computational cost of these different tasks that we have to do. So the fast Fourier transform, which is the cornerstone of the plane wave code, scales like the system size times the logarithm of the system or the grid size. And because we need to do this for all orbitals, this gets an additional factor of the system size. So this is so the grid increases as you increase the system, and the number of these orbitals increases as you increase the system. So overall, the plane wave code scales like n squared, and then this logarithm n factor is not so important. And then the next step is applying this potential in real space. So here we have the advantage that the potential in real space is just expressed on this grid. So this is just an element-wise multiplication. So this scales linearly with the number of grid points. And then again, we need to apply the potential to all the orbitals, which gives another factor of n. And again, this leads to an n squared like behavior. And finally, we want to project this orbital onto these projectors in the PW sphere. And then this projection has now a cost, either if you do it in reciprocal space linearly or in real space, it's constant. And you can swap between the two techniques with this L-real flag. So for large systems, we recommend that you use this L-real flag to get this lower scaling method, which only scales like n squared. But for small systems, the prefactor means that this conventional projection method with matrix multiplication might be faster. It's also more accurate. So if you want to have very accurate calculations, you might want to project in real space, in reciprocal space. And then the next parts are then diagonalizing the Hamiltonian, then rotating in the subspace. So we calculate the Hamiltonian in the basis of these orbitals, and then so projecting the Hamiltonian on these orbitals is a matrix multiplication, which scales cubically in the size of these matrices. Then we diagonalize this matrix, which is another cost that scales cubically with the system size. And finally, we rotate with this U matrix in this subspace. And again, this is a matrix-matrix multiplication. Again, this whole thing. Now, we saw in the previous slide that most of the terms scaled like n squared. And here, all the terms scale like n cubed. So why was I so focused about the FFTs in the beginning? So to understand this, you need to be aware that there are also prefactors involved. So even though this, the methods on this slide have the highest order in the scaling, they still have a lower prefactor than the FFTs. So because we do so many FFTs, usually this n squared cost of the FFT still wins out. And you can actually see this if you measure the timing of the code for these different contributions. So I will show you now a busy plot with a lot of figures. So let me show you how you can look at this particular graph. So this line at the bottom is the ideal scaling of the FFT. So this is an n squared log n plot. And if you now compare the time or measure the time of the full self-consistent cycle relative to the time that it takes at a system size of 256, then you can see that this follows relatively closely this n squared log n behavior. And whereas the other part, this orthogonalization part, you can see that this scales significantly worse. So this is this n cubed behavior that I talked about. However, if you then compute the ratio of those, you will see that actually, even though the scaling of this part is worse, overall the red line, so the prefactor of this red line is still much larger. So in the end, it takes about an order of magnitude more to conduct this self-consistent iteration compared to the orthogonalization. So in the end, if you go then with the system size, the orthogonalization becomes more and more important, but even in very large systems, it's still a factor of 5 more expensive than the orthogonalization. Okay, so this concludes the first part of the lecture, and now I want to talk a bit more about how these tasks are parallelized in VASP. So let's focus again on the Kuhn-Sham equation, and now look at different parts to understand where parallelization options can come from. So first we can see that here we describe more than one electron, right? So you can, for every atom, there can be multiple electrons, and total you get a number of bands. So the first thing you can do is you can set you can choose to run a certain number of bands on each CPU. And so probably you want to have multiple bands on each CPU, but you can use CPUs to parallelize over this band loop. Then the next thing we see is that we have here these grid points. So the grid points essentially correspond to these FFTs that we need to do, so you can parallelize the FFTs. And in VASP, this is controlled with the in-car tag ncore. So if you set this in your in-car tag, you will parallelize over the FFTs. Then another thing you will see here is the Bloch vector. So all these bands, we want to evaluate this at multiple k points, so we can parallelize over those k points with the in-car tag kpar. And finally, in some situations, you even want to run multiple independent VASP calculation. One such example would be the nudge elastic band method. And if you have this case, you can run this multiple VASP calculation with this image tag. And this gives you the most embarrassingly parallel way to add more CPUs to attempt your problem. So you can parallelize over the band loops, the grid points, or the FFTs, the K points, and over independent VASP calculations. And this gives you then the total number of CPUs. So let's dive a bit deeper into these individual options. So let's look at the distribution over the orbitals, over the bands. So in this case, I will assume that we have a total of 6 bands. And now the default option of VASP is to parallelize over bands. So let's say we use 2 CPUs to attack this problem. Then what will happen is that half of the bands will go on one CPU and the other half of the bands will go on the second CPU. And then they will be distributed in this particular way. And then we can think about when we need what kind of communications this entails. And then we know that essentially for the update step, where we update a band, it's independent. So each band is more or less treated independently. But when we want to diagonalize the Hamiltonian, or if we want to orthogonalize these bands, then we need to communicate. So then we need to understand the content of all the bands. And actually we will redistribute the bands to perform this orthogonalization, which something I will talk about in more detail later on. Then the other option was to parallelize over the plane waves. So now an alternative is, again, we have two CPUs, but now we set in the incl file ncore equals 2. And this leads them to different distributions. So in this case, all bands are shared by the CPUs, and half of the G vectors of this band is on one CPU and the other half is on the second one. So this, of course, requires more communication. So when we want to do a fast Fourier transform, we need the information from all G vectors. So essentially, this means in every FFT, there will be a communication across this number of bands, or across this band. And then the same will happen for the second band, the third band, and so on. But you can also combine those two methods. So you can parallelize over both the band index as well as the grid. For example, you could now use 4 CPUs, and you only need to set ncore. But if you set ncore to 2, it will automatically again use the remainder of, or the remaining factor to parallelize over bands. So with 4 CPUs and ncore set to 2, you will get a kind of this setup. So you have 2 CPUs working on this set of bands, 2 CPUs working on this set of bands, and within each of this subset of CPUs, they will split each band individually. So then you get some kind of bit local communication here in this group to do the FFTs, and then some local communication here to perform the FFTs on that, and then some communication between those two groups to perform orthogonalizations and diagonalization. And yeah, so if you have larger systems, you might want to combine those two parallelization options just to get a bit more performance. So typically what you will see is that for large systems, it's often more efficient to use multiple options to parallelize instead of just a single one, because it's often, there's some overhead with this parallelizations. If you go to very extreme values, where every CPU would only deal with, let's say, 2 bands, then this overhead would eat into your performance, and then it can easily be more efficient to instead use different parallelization option that you haven't used before. Then the next option we talked about was K-points. So the distribution over K-points is relatively simple. So if you know how many K-points your system has, you can easily use the same number of processors or CPUs, or actually groups of CPUs potentially, as this K-par option. So within each K-point, you can again use both these other options. So you can use can parallelize over bands, you can use ncore to parallelize over the FFTs, and then in addition over the K-points. So one disadvantage of this approach is that you don't know a priori how many K-points you want to have in systems if you have symmetry. So you might want to run a calculation just until the K-point mesh is generated, and then perhaps stop it again, look how many K-points you have, and use then that to set your K-par variable. Also note that some of the data is duplicated. So this method of parallelization is very efficient, but in terms of CPU usage, but requires some additional memory compared to the other ones that reduce the size of the orbitals. Okay, so now let's come back to this, how the two orbitals, or how these orbitals are transformed in the subspace diagonalization. So when you look here, if you want to calculate overlaps between different bands, you can see that the disadvantage is here for every component has more or less a different color. So if you want to, let's say, take a dot product between 2 of those, you will see that everything requires communication. So this is not so ideal. And actually, we want to avoid this. So what we do is we first redistribute those bands to make afterwards the subspace diagonalization more efficient. So we go from this kind of pattern to this distribution where every band is distributed over the CPUs. And then you can see if you use this kind of pattern, always the same G vectors are on the same CPU. So I visualize this on the next slide. So you can see if you now calculate an inner product between those two bands, then you just need to you don't need to communicate. So you can perform this inner product on one CPU, and then you do the next few G vectors on the next CPU and so on. And in the end, you just take a sum of all of this. So there's no communication required except for a single MPI reduce at the end, which is much more efficient than if you had to send the whole orbitals or multiple orbitals potentially to other CPUs. Now let's move on to our FFTs. So in our code, we actually use a customly written parallel FFT method to go from the plane wave sphere. So actually you know that in the in-car file, you set a plane wave cutoff, which defines a sphere of G vectors that we want to use. On the other hand, for the FFT, we have continuous grid or discrete grid in the whole cube. So now we need some method. So in principle, of course, you could use an FFT where you use all these G vectors and just set everything to 0 that is not inside the sphere and then use a normal 3D FFT. But you can see that actually the sphere is much smaller than the grid that we use. So this will also result in some wasted resources. So what we do instead is we go in sequence, first from this cube to a cylinder shape. So here you can see that we transformed along one of the axes, and then the cube turns into a cylinder. So now this still can be done on a single CPU without communication, even if you parallelize over the grids. But then when we want to add the other two dimensions, we need to communicate the different G vectors. And when doing so, we can then expand from the cylinder to a plane. So this is now a subset of the whole grid. And then the last step, we communicate again, and then we can perform a Fourier transform to the full cube. And yeah, and then we have in real space, we can, for example, compute then the density and sum over all orbitals. So the advantage of this custom SFT is that we use about 1.8 times less 1D FFTs. And the disadvantage is that there are some communications involved going from this G to R grid. But speed up is still reasonable, so that for all medium to large FFTs, it's still more efficient to use this custom FFT. And as these are the systems where you're probably most worried about the compute time, we typically recommend that you use this custom FFT. So let me now move on to a new parallelization method that became more relevant in the recent years, which is using GPUs. So in VASP 6.2, we introduced a new feature, which is the OpenACC port of VASP. So we had a previous VASP GPU port based on CUDA, which is now deprecated. So you should use this OpenACC one instead, which covers many more features. So the advantage is, from a development perspective, that this OpenACC resides in the same code base. So it's easier to port new features and keep them all up to date than if you have two code bases, one for the CUDA version and one for the, let's say, regular CPU version. So what is already available in this OpenACC is more or less everything with density functional theory. So all kind of exchange correlation functional hybrid functional, van der Waals functionals. You can do linear response calculations. Both is implemented, so you can do either finite differences, which just relies on energy calculations. So essentially kind of trivial extension of the local DFT and hybrid calculations, or you can even do density functional perturbation theory. Both are ported with OpenACC. What we are currently working on is an OpenACC port of the GW method. So this will probably happen in one of the next releases. What you should be aware of is that even if you use this method, there will be still some part of the code running on the CPU. So you might still care about how to set it up efficiently also on the CPU side. So because always some communication happens through those CPU branches and some computation happens on the CPU. What do you need to do to run this new version with OpenACC support is to compile the code with a compiler that is supporting this OpenACC standard. Currently, we only support the NVIDIA compiler there, so in VFortran. In the G-Fortran community, there are some works on going to kind of recent OpenACC standard, but this is not done yet, so we don't recommend. I mean, you can experiment with this, but we do not recommend it at this stage. And in addition to an OpenACC able compiler, you also need to have an CUDA MPI. So the MPI needs to know that there are GPUs that you want to use for parts of the calculation, so that the communication properly communicates the data from one GPU to another, where this is necessary. If you have large systems, we recommend that you use the NVIDIA Collective Communications Library for communication, as we found that this is more efficient. It allows you to use an asynchronous pattern which hide the communication with communication, which hides the communication behind calculation. So you can do both calculation and communication at the same time. One restriction of this, though, is that you only use a single MPI thread per GPU. So you might still use OpenMP, but one requirement is that you only use a single MPI thread. So for smaller systems, you can actually then deactivate this NCCL. The advantage is you can even deactivate this at runtime, so you can have one compilation of your code, and then depending on the system size, you either deactivate it or not. If you deactivate it, you can then run multiple MPI threads per single GPU and then parallelize over these MPI threads. And note that this requires that you compile with this multi-process service, which is also part of this NVIDIA performance library. So how does this, how did we realize this GPU? So let's disadvantage of this could be that you prepare some data for your GPU and then you communicate it. This would take some time, and then the GPU will do something. You go back, calculate the next result, and port it, push it again to the GPU. But actually in OpenACC, there are some options that you can use some asynchronous patterns. So often in DFT, we want to do a lot of things that are more or less independent. So we want to calculate multiple bands. And if you want to apply the potential to one band, we don't care about the other band at that stage. So essentially we can prepare, let's say, the second band before we send it to the GPU to perform some operation on it. And if you do this kind of asynchronous pattern, what happens is that you can use the GPU better. So this is essentially what you always want. So if you look at some profiling of this GPU, well, the ideal scenario is always that your GPU works all the time, because on those GPU machines, this is where you have the real compute power. And the NCCL allows you to have the same kind of pattern between different GPUs. So you can communicate the data, and again, get this efficient way that all the GPUs run all the time. So I mentioned that you can combine GPU, even this NCCL, with OpenMP. So recall that some of the code still runs on the CPU. So if you want to get the maximum performance, what you can do, even if you run a single MPI thread, you can still spawn some OpenMP threads, and then this will further enhance the compute time for very expensive things. So, okay, so what performance can we actually get from this? So this is a system where we tested a hybrid functional on a vacancy of a supercell of silicon. And for comparison, here's the time that it takes to run this calculation on this, or this is the time that you get for a single CPU, and then this is how much faster calculation is if you run it on 1 GPUs to up to 8 GPUs. So you can see even by using just a single CPU, we get almost 5 times faster. And then this scales, and by using more and more CPUs, we can get close to 30 times faster by using one node. So here in this particular node, you have 1 CPU attached with 8 GPUs. Okay, so the last part of the lecture will now focus on the system considerations. I will focus both on the physical system. So what kind of considerations do you need to take into account when depending on the number of bands and capons and so on that you have. And then also hardware considerations. So how this determines what kind of parallelization options you should choose. Okay, so let's discuss first this default parallelization, the band parallelization. One important thing that you need to know or you need to remember is that VASP will adjust the number of bands to match your parallelization. So then, if you don't set any other parallelization options, the number of bands will be a multiple of the number of CPUs that you use. So this means sometimes what you can see is that the calculations change, and essentially what you add is then more and more orbitals as you increase the number of cores. So you don't want to use more CPUs than you have bands. Otherwise, you will just start adding more and more empty orbitals that will not really improve your self-consistency anymore. So when you kind of saturated this band loop, you will, so this number of bands, number of electrons that you want to compute, you cannot get faster by adding more CPUs. Then you need one of the other parallelization options. But in principle, you could use, you could use the number of CPUs equivalent to the number of bands. This is typically not a good idea. So what you typically want is that the number of bands divided to the threads working on these bands is some integer larger than 1. So the reason is that some of these algorithms just converge faster. It's easier if you work on multiple bands at once than if you work on a single band. It also leads to a better balance between work and communication. Otherwise, you need to communicate all the bands between all the CPUs. So that's what I mentioned earlier already. Typically, it's never a good idea to fully saturate only one parallelization option. If you have a lot of CPUs, it's better to distribute a bit between the different options that you have available. Furthermore, there's also an advantage of using multiple bands. There's an in-color variable called insem for blocked algorithms. So blocked algorithms in particular are the default algorithms that you will use most commonly in VASP, like normal, which is a Davidson, or very fast, which is this DIS, or the mixture of both, which is fast. And so the advantage of using this NSIM means that you, instead of dealing with one band at a time, you deal with multiple bands at once. And this means that a lot of this application of something on a band becomes, instead of matrix vector multiplication, becomes a matrix multiplication. And those are typically faster in this blast calls. So you get a bit of speed without, I mean, it's not a parallelization option per se, so it's just a way to make your code faster. And on GPUs, this is even more pronounced. So for GPUs, you might experiment with setting larger values of nsim to get even more performance. And then let's focus on the k-point parallelization. So the k-point parallelization will split the number of k-points, distribute them into k-part different tasks. So you should be aware that if you use a k-part that is not a factor of the number of k-points, you will just waste compute time. So essentially, if you have, let's say, 12 k-points and you would use 8 CPUs, then 4 of them would have nothing to do in the second iteration. So it would, in that case, be better to use a k-power of 6, because that would match with the number of k-points that you have. So I mentioned already earlier that you don't know necessarily a priori what this number of k-points is. So you might want to investigate first by running a very short calculation or a system with the same symmetry to investigate what number of k-points you will actually get by VASP, and then use this to base your parallelization setup. In principle, this is an embarrassingly parallel, almost embarrassing parallel setup. So if your memory allows, recall that some data is duplicated between different processors in this case. But if your memory allows, you can set the k-part to the number of k-points. There's no other restriction here. Let's look now a bit more in the typical hardware that you have. So in this HPC sites, typically you have multiple compute nodes, and on each compute node you have done package with multiple packages with each few cores on them, and then so you have some communication between the package and between the nodes, and then there you have some memory communication with the random access memory. So now, how would you set these calculations up? So this is the lowest level of communication. So here, what you want is that, so this is where we use the FFTs. So this means that this corresponds to our n-core parallelization level. So what's important here is that you need to remember that essentially the further you travel here in this graph, the more expensive it is to communicate. So within here, the local package, it's very efficient, and it will be a bit less efficient between the packages, and then even less efficient through the interconnect to a different node. So this means that you want to set up your n-core such that it matches to this hardware setup of your calculation. So if you have a system like here where you have a package size of 4, you could, for example, use an n-core of 2. That would match up nicely with this setup, but you would not want to use something like 6, where you then scatter one group over to the next node. So other setups that might work are 4, so this would nicely fill one package, and then if you go to 8, you would already fill the whole node. So this might still give you a nice performance, but it will be probably already not as efficient as using 4. But of course, if you have very expensive calculation, it might still be the way to go. So this brings me to a slide briefly discussing what kind of calculation or parallelization limits you can use, and how far can you push this if you have a really expensive calculation and you want to get the maximum VASP has to offer. So what you can do is you can do an n-core setup. This depends, as I discussed on a previous slide, on the size of your node and package. So you can use as many n-core as you have node or package, but note that for some codes, in particular the GPU version or OpenMP version, you should not use n-core. Actually, the code will enforce that n-core is 1. And then you can use the k-point parallelization. So this depends on the number of k-points. And if your memory allows, you can use as many as you have k-points. If you have independent systems that you want to compute, you can use as many images as you have systems. And then this brings you then to the total number of CPUs. This is the product of all of those times the number of bands divided by a small integer. So this is, we discussed that this NCIM, so the number of bands that are treated in a block-wise fashion, and even that you want to, for GPUs, want to increase this number. So kind of this small integer should be similar to this number. So this is the absolute maximum. So you might want to have lower numbers for all of those, but for some systems where you really want to push the boundaries, this is the way to how far you can go. One other thing for large systems that you also should consider is setting the switching on the real space projection method. So the advantage here is that we do an FFT to real space, and then we can do these projections on in the PW spheres in a smaller. So it's one order of less in the number of system size. So essentially it's an element-wise multiplication instead of a matrix multiplication. And this makes it faster. Another thing is if you have very large systems, typically you also have very few k-points. And if you have only a gamma point calculation, then you can switch to the gamma point mode of the code. This will change some orbitals and make change the orbitals to be real, and a lot of FFTs and matrix multiplications can use then versions where you know, okay, if this quantity is real, you can switch to, say, from a C-gem to a D-gem, or you can use do two FFTs for the price of one. So if you only have a gamma point, then please use this gamma point version. So this brings me to now one of the, let's say, more unfortunate parts that you need to consider is when you do this MPI parallelization, is this, you need to be aware how these MPI ranks are actually distributed on the node. So more or less a bit earlier when we discussed NCore, I discussed kind of the ideal scenario, which was that the nodes, the ranks, the CPUs are placed like this, that first one package is filled, then the next package, and so on and so on. And in this case, the ranks with the numbers that are close are also close on the package. But this is not necessarily the only option that you can do. So this depends how the MPI is set up. So during the installation, there's some configuration options, how this MPI will place the ranks by default. And one alternative might be that you distribute over packages first. And you can see that in this case, while the two CPUs are still on the same node, once you start using NCore 4, you will already communicate via the interconnect, and that will slow down your code. So this is something that you need to check. If something like this happens, you need to find out how you tweak this with some MPI setup to enforce the correct placement of the ranks. There's even a reverse scenario where this is where you distribute the ranks over nodes first and then within the packages. And yeah, if you encounter this setup, you would not even probably see a real speed up if you use NCore 2, because that would then go to directly performing the FFTs over this interconnect. And I mean, there might be still valid reasons that a HPC site might choose this setup, because more or less in terms of memory, this is more efficient. If you don't use the full node, you can see you would only have two ranks, and then they would each have the maximum DRAM, but then you need to correct for this again if you want to use this with the full node. And then you need to pass some variables to the MPI. Okay, so how fast is this now? when you use these different setups. So here you can see a scaling plot for this larger system of silicon. So this is a strong and a weak scaling. So strong scaling means increasing the system size with the number of CPUs, and ideally you would see that this does not significantly change the compute time. And then the weak scaling is at a constant system size, you increase the number of CPUs that you use. And you can see that the larger you make the system, the faster, the further you can push the computing, the parallels efficiency. And this applies both to local density functional theory. So here you can see that for this defect in the magnesium, you can go to a large number of thousands of CPUs and still have a parallel efficiency of over 70%. And the same applies to as well to hybrid density functional theory. Again, studying this defect, and you can see here again 1,000 CPUs, 80% efficiency, and you still get a speed up, though not as large if you go to 2,000 CPUs. And then another thing is this ACC port that we also discussed. So here is the performance of 8 of those nodes. So each of these nodes has 8 GPUs. So we go here from 8 GPUs to 64 GPUs. And you can see that scaling this reduces the parallel efficiency only to about 75% or 80%. So this is a very reasonable time for this hybrid functional calculation. And now you might wonder how this actually depends on the communication. So if the communication between the different GPUs is the issue, and for this we did another test where instead of increasing the number of GPUs, we just increased the number of nodes, but left the number of GPUs constant. So we went from 1 GPU, from 8 GPUs on one node to 8 GPUs on 8 nodes. And essentially the time is more or less constant. So this tells you that there's so this really shows you how efficient this NCCL communicates between the different nodes. So there's really good hiding of the communication behind computations. So we barely lose anything by going to more nodes. Some final tips now on how to compile VASP. So if you want to compile VASP for CPU implementation, you should make sure that your FFTs are as fast as can be. On Intel CPUs, this means that you want to use the MKL library, which is often the fastest one that we've found. So in many tests, the fastest that we found. If you have large systems, you will also want to activate ScalaPack in addition, also parallelizing the LAPA calls. And if you can, compile with this AVX2 compiler instructions and libraries, then you might get an additional 20% speed boost. If you compile for GPUs, note that at the current stage we only support NVIDIA systems. You should use this NCCL for large systems, which hides this communication. And if you want to really get the most speed possible, you can also use OpenMP to make the CPU side code fast as well. So this brings me to the end of the lecture. So we discussed the different tasks in VASP that we face, how we parallelize them, and then how to choose these parallelization options based on the physical and hardware system that you have. Thank you for your attention.
Great. Thank you, Martin, for this talk. I hope that setting up the calculation efficiently now sounds like a less daunting task to everyone. Beforehand, I collected some questions, so I would appreciate if I can ask them now. So let's see. What causes the error LAPAC routine CPOTRF failed?
Okay, so there are two common reasons why this error occurs. So the most common one is probably an error in your setup. So very often it's that you some positions of some atoms are very close, and then it cannot properly construct this potential. So what you want to do is visualize your structure and see if there are any atoms that are very close together. And if you check that your structure is set up and all the distances check out, then the next thing you can do is play around with the pseudopotentials. So this, of course, you might not always want to do that, but
so play around in what sense?
In the sense of replacing it with one of the other ones. So you can replace a standard one with a GW one. I mean, this is, yeah, it will not happen often, but this might be one way out because it's slightly different parameterization of the atom, so it might not result in the same error. And otherwise, I mean, this is a system where you, I mean, essentially you end up with a system that is linear dependent. So you can turn some other knobs of VASP, like cutoffs and so on, but I mean, that's not something that we commonly see working. So the most common issues are really the pseudopotentials and the positions of the atoms. I mean, you're happy, of course, to, if you encounter this and played around with all systems, to post a question in the forum. Then we can perhaps give you some hints how to solve this. But yeah, and often just looking at the structure, you see something already that perhaps you swap the position of two atoms and then suddenly it doesn't work anymore.
Okay, then maybe a question about parallelization. How does parallelization affect the total energy? A user reported that actually there was a change in the first decimal point behind in the total in the first decimal point. So how can one test which one is the most accurate setting for this calculation?
Yeah, I mean, often what you see here is that actually when you change the parallelization, that the setup changed. So what a good idea here is to investigate your outcome file. So compare the outcome files of the two different calculations, and you will often see that the setup changed. So for parallelization in particular, what happens is that I mentioned that the bands is a multiple of the number of CPUs that you use. I mean, if you use the default parallelization. And what you can see is that you use more bands in one case than in the other. And when you change the number of bands, your system can take different routes to find the minimum. And in particular for more complicated systems, so complicated in the sense of the potential that you use. So let's say you use magnetic system, or use LDI plus U, or use hybrid functionals, then it's not necessarily so that there is only a single minimum of the DFT calculation. So you can have different magnetic states that are reachable, or different orbital states, orbital magnetizations. So this is depends really on your setup. And what can happen is that you run into one of these local minima with one of the calculations, depending on the number of bands that you use. But of course, what you can always do in the end is compare the total energies. So if you have multiple of these runs, in principle, the lowest energy should be your ground state, or the lowest state that you found. It's the most stable configuration.
I see. So actually the empty bands wouldn't change the total energy, but because I might end up in a different local minimum, the system, so the boundary conditions basically changed in that sense. Okay, so another question would be, is the OpenMP mostly of interest for saving memory or nodes?
I mean, the OpenMP also has some performance aspect to it. For, let's say, a conventional system, you will probably not care so much about using OpenMP or NCore, but some of for some parts of the code, you might prefer OpenMP over the encode. So I mentioned already earlier with these GPUs, it's not really possible to use. It's not really possible to use encode larger than 1. So in that scenario, you might just want to use OpenMP because it's your only option. And also sometimes it's beneficial in terms of the memory bandwidth. So perhaps the OpenMP can help you there. But it's hard to make general rules here. So yeah, depends on your system.
I see. So perhaps another question on error messages from a user. So is there a website or some documentation where we can look up the VASP error messages and warnings to get an idea about what causes the problem? And if not, is there a plan to make such a resource available?
I mean, at the moment, there's no list of error messages other than in the source code. I mean, we hope that the error messages should give some guidance on how to overcome this issue. So, I mean, our goal is to continuously improve those error messages. So if we encounter an error message multiple times, that we give some better guidance how to avoid this error in the future. So, I mean, one thing I can recommend is that if you encounter an error that you don't understand, that you post the question in the forum, because I mean, this is how we realize that, okay, perhaps this is an error that multiple users encounter. So then we can find out, okay, can we do something about it? Can we make it not produce this error? Can we write the error in such a way that it's clearer for the user what they should do when they encounter this error? Yeah, so I think the forum is a good resource.
Yeah, very good point. So this is a good opportunity to say a big welcome to the forum, and please join the discussions there. And maybe actually someone else asked a question already and you find the answer there to your problem as well. Yeah, so let me ask for a final takeaway message. Suppose I'm new to running VASP calculations and I'm a bit overwhelmed by all the details about computer architectures and parallelization methods. How can I start to optimize my calculation for efficiency?
Okay, I mean, for a user, I think what you need to be aware of these different options that you have. I mean, I give you now some lists in this lecture, what kind of options you have, but there's no, let's say, strict rule what will work for your system. So this really depends. I mean, there might be systems where you have relatively large unit cells and then a different option. So say you study molecules, then some different method might work than for a thing where you have very high energy cutoffs or a lot of K points. I mean, this really depends on the system, what is the optimal choice. So what one can give perhaps as a rule is, or as an idea is that based on this, what you know, what is available, you can make tests. So typically in DFT, we always run multiple calculations of the same thing. So you might want to study multiple materials with similar setup. You might want to run long relaxations or MD simulations, where you run the same calculation over and over again. So what you can then do is, let's say, do a first few runs with slightly different setups, choose a few different calculations with one where you use more where you use your CPUs to parallelize over K points, one where you use N-core, one where you use the default band parallelization, where you mix these different things. And this way you can explore and actually measure the timings. And typically those timings are quite reproducible. So you really need to focus on the per iteration time. So that it takes, so sometimes the different calculations might take different number of iterations to converge. But if you account for that by dividing through the number of iterations, you will get some measurements, actual measurements for your system, which is the best setup for you.
Mm-hmm, mm-hmm. Yeah, that's a very nice closing thought. So testing, testing, testing. Thank you, Martin, for the presentation and also for taking some questions in the end. And yeah, thank you to the audience as well.
Thank you.